Juste quand on peut démarrer, et puis j'imagine que c'est bon. Monsieur, bonjour. Okay, good afternoon, everyone. It's a pleasure to see you here. Actually, you're not alone, since we also have a virtual audience. Well, I do not have the exact audience in front of me, but I think we are talking about 15 people currently connected to the workshop. So, well, you know, the way we discussed initially this workshop, I think this should be quite interactive. So just do not hesitate to interrupt us, to, you know, ask questions also on the chat online, and we will do our best to, well, to provide an answer, I guess. I just need to find my slides back. So, well, basically this workshop is about simulating 5G for connected mobility. So what we are going to present today are, well, 3 topics. So we are all working at least. So on my side, my name is Sébastien Fay. I'm a senior research and technology associate working specifically on 5G and 6G technologies for well-connected mobility in that case. And then I will also share this session, let's say, with Kiang. Maybe Kiang, you can say a few words about yourself.
Okay, so similar to Sebastian, I'm also a senior research scientist analyst. So my background is mainly cybersecurity. So with some joint projects now, I'm doing some research in the cybersecurity for the CCM and mobility and 5G as well. So this is my background.
So Kiang, you will present in a second time. Well, you will be a bit more specific, let's say. So on my side, I will more introduce, you know, what we are doing, at least an overview of the different technologies, simulation, software solution we are using. On your side, it will be a bit more focused on security, privacy challenges, and how to solve them, basically, in the context of, you know, when we use simulation tools and so on. And then last but not least, well, Ian, maybe you can.
Yeah, my name is, hi everyone, thank you for being here. My name is Ion Turcanu. I am a research and technology associate at least, and I'm working mainly on connected vehicles, vehicular networks, intelligent transportation systems, and related topics, and how next generation cellular networks can help in this domain. So today I'm going to showcase some simulation tools that we are using typically to implement our communication protocols, our solutions, and we are going to see that live. Thank you. Yeah.
Yeah, so this will be the last session, indeed the most interactive one, probably, where you will see tools in live. So, well, I'll just start by my presentation, basically. So on my side, I just want to, let's say, introduce an overview of what we are talking about when it comes to simulating connected mobility. Here we are playing with quite huge keywords, and I think this is the right context, you know, to talk a bit about what is behind, what can we do today, what cannot be done with simulation, and what are we working on specifically, at least, you know, so that you have a few examples, a few use cases that might be useful for, well, the audience. So basically, I will just start with this video. So it's not an old video game, okay? It's a simulator called Sumo. It's an open source simulator. My colleague will show you more details about that. But this is basically what I was working on 10 years ago when I did my PhD thesis. So it was, well, 10 years ago, actually. So as I said, it's a mobility simulator. Here you can see a few vehicles, and you can basically see a grid of intersections. So at the center of each intersection, there is a traffic light. This is not visible here because the screen is a bit too tiny, but there are traffic lights, and you can basically see here that there is no coordination, there is no communication, there is nothing. Okay, this is just a purely artificial data set that has been generated through Sumo. So, well, basically what I did, this was my mission 10 years ago, was to try to optimize a bit this scenario. So basically what I did to optimize this scenario is to deploy wireless sensor networks around the traffic lights so that we can interconnect the traffic lights and the vehicles, and then try to exchange data in a very realistic way and, well, optimize a bit the situation. So this is basically what I did, I guess, 10 years ago. And you can see here that, well, all the traffic is, well, fully optimized. The traffic lights are fully reacting to the vehicles, and they are taking into account all these parameters in a, well, nice way, let's say. So with that, we can reduce the pollution, we can reduce the waiting time of the users, and of course we can increase the overall efficiency of the traffic management system. The only issue is that, well, it was 10 years ago, right? So it's not super realistic, it's not super representative of what can be done today in the reality. So, well, the main message, I mean, something I would like really to focus on a bit today is what has the scientific community proposed since then. So 10 years ago, we were playing with this kind of artificial data sets, but today we have access to many data sets, to many methodologies, to many software solutions, and this is basically what I would like to share with you. So LIST is working on that. We are not the only ones, and I think this might be, well, useful to share that kind of information with you. So the first aspect that has, well, that is actually way, let's say, that is way better, let's say, than 10 years ago, it's the user demand, okay? So as you saw at the very beginning, the user demand was totally artificially generated. It was not realistic at all. So definitely this is not convenient when you want to plan, for instance, the deployment of a 5G antenna and then study the impact on a connected mobility application. So here you can see a very realistic, well, simulation scenario on Esch-sur-Alzette. So here it's specifically a part of Belval. And in this kind of simulation, you have everything. You have buses, you have cars, you have pedestrians, you have even trains. You can really simulate the daily mobility patterns of, well, let's say a given area, so that it's super realistic. So again, this is an open source tool called Sumo. We will get more details just after. But just to show you that, well, with the tools and the methodologies, the data sets we have today, it's possible to reproduce this kind of scenario quite easily, and then use it as an input for research projects, but also for companies, for instance, companies that would like to test or verify their own applications before actually deploying them. So this is the, well, one first aspect. Today it is possible to do that kind of simulation. For those who are not familiar with this world, let's say. Then this is just a second example of Luxembourg City. So this is a scenario that has been proposed by the university a few years ago. And here you have also the daily mobility of, well, the traffic patterns and, well, the buses, cars, and so on, a realistic topology as well on the city of Luxembourg. So typically we are using this kind of scenario to validate, to test, to let's say, experiment different kinds of, well, approaches. So, for instance, I was mentioning traffic light management at the beginning of my presentation. Here, it's a typical scenario that can be used for that. So, what is the impact, for instance, of deploying this traffic management algorithm when compared to this or this or this strategy? And then you can directly measure different metrics like wasting time, duration of the trip of the users, and so on. So this is, yeah, really the kind of tools that, well, might be used easily because it's open source by the scientific community and, well, the industrial community also, I would say. So this is only the, well, the user demand part, the mobility part, but then, of course, in connected mobility, you also have the word connectivity. So here, for instance, you can see a concrete software solution that has been well developed by Forsk. So it's called Atoll. This is a software that is used, I think, by most of the network operators in Europe. Maybe not all the network operators, because of course then you have other solutions similar to this one. But, you know, it's just to give you a feeling of, you know, the technologies, the software solutions that exist when an operator needs to deploy, for instance, a 5G or a 4G antenna or a Sigfox, well, relay. I mean, they are basically using this kind of tool before the deployment. So here the ID, so still you can see Belval and a bit of Esch-sur-Alzette. So here, for instance, you can see 4 different base stations. And each of these base stations is equipped with, well, a set of transmitters. And basically here it's possible to, well, to to deploy any kind of transmitter. So you can deploy, for instance, a 5G transmitter, a 4G transmitter with any kind of characteristics. You can configure your propagation models. You can really go deep in let's say the communication technology, so that you can then experiment and decide about the best location, for instance, for your antenna, or let's say the best parameters for your transmitters. So this is a network planning and design tool. This is commonly used by the network operators. And as a research institute, we are also using it to, let's say, test, verify our models. So for instance, at the moment, we are working on optimization techniques to optimize the location of the antennas, the configuration of these antennas. So of course, if we would like to have the same baseline, let's say, than the network operators we will rely on that kind of tool. Just to give you an example. And then, of course, it's not only about 2D. So we also need to play with 3D data. And this is what you can see here. It's a very simplified model of Belval. And here what you can see is just the shape of the buildings, basically, that are in Belval. So we only focused on this particular area just to, give you one message here that, of course, we need to consider 3D data when we study network propagation and so on, since obviously the antennas are not, most of the time deployed on top of a building, or let's say with a given height. So we need to, let's say, consider all these structures and see the effect, the impact of, deploying an antenna at a particular location, and the effect on the propagation model. So again, it's just an example of how far we can go when it comes to simulation. So now coming back to what we are doing, at least, I think one important message, in my opinion, many important messages, then depends on you, of course, to take them or not. But we are currently working on a project. It's called 5G Planet. This is a project that has been funded by the SMC. And here, basically, we have 7 months to develop a decision support system for the general public. So meaning that we need to develop an awareness raising platform, as I clearly indicated here in the slides. And the objective would be to rely on all the simulation tools, the data sets I previously presented, so that we can explain to a very general audience what is 5G, what is connected mobility, how much connected mobility can be useful, for instance, for your daily, let's say, habits and so on. This is something that is, in my opinion, quite useful, because today we are talking a lot about 5G, but in the end we do not really know what is 5G, I mean, as a general audience, I would say. So I think this is also one of the missions we have, at least, to try to communicate, to disseminate a bit more about these new technologies and see exactly how this can impact the, let's say, the general public. So this is a concrete project. We will use simulation tools. We will also use emulation solutions, so that let's say, the audience can directly interact with let's say, the simulation solution. So we have plenty of ideas in mind. This is currently under development, and we should release that in February next year. So, if you are interested, of course, I would be quite happy to discuss that after the workshop. And what we would like specifically to do here through 5G Planet is to go, let's say, a step further. So not only propose a 3D visualization with, let's say, simplified shapes of buildings, but really go deeper. So basically here, what you can see, it's a 3D model of Belval. So this is a 3D model that has been built with Nomoco. This has been built by Nomoco, a company. And what you can see here, this is all the environment, all Belval modeled in 3D. Here you have a resolution of about 2 centimeters, which is spectacular. I mean, it's very small. And what we would like to do in the future is to use this kind of data to combine this kind of data with the previous tools, with the previous methods, with the previous approaches you saw, so that we can really propose a platform that, let's say, talks to everyone, just to show you what we are working on at the moment. well, we just finished the presentation by just showing you a few projects that make use of these simulation solutions. So one project is called 5G Emit. It's also a project that has been funded by the SMC. And here it's, well, so the objective here is to create, let's say, a network planning solution to, let's say, optimize the deployment of antennas while considering the exposure on the electromagnetic fields. So you probably know that, well, the network operator cannot deploy as it wants a 5G antenna. We have regulations today. We have limits on the electromagnetic field exposure. And, well, this, of course, if you do not consider this limit, then you cannot deploy an antenna. So what we try to do in this project is to, let's say, propose in the best possible way. Sorry, a pop-up arised. So to propose to, well, the most optimal deployment strategies, let's say, while considering these exposure limits. So we are organizing a workshop dedicated to that tomorrow. So if you want more details on that kind of project, yeah, please join us tomorrow. So I will not spend too much time here, just showing you this additional visualization interface. So here we are really taking the 3D model of Belval, okay, so you can see all the buildings. And what we try to do is to compute the exposure of, the electromagnetic field exposure of each transmitter, so that we can then really play with the position, with the parameters of the antenna, and decide about, well, let's say, what is the best positioning for these antennas, what are the best parameters, so that we can minimize the exposure and at the same time, well, let's say, maximize the performances of each of these antennas. Yeah. And then I can see the time passing, so I will maybe try to accelerate just by presenting a very last project. So this is not directly, about 5G. This is about waste management, and we are not using 5G, but we are using Sigfox. And well, I very much like this project because it's a project where we actually deployed concrete sensors. In Luxembourg, we are collaborating with Polygon, with Post Telecom as well. And here, the objective we had was to try to optimize the way Polygon works. So you probably know that Polygon has a waste management service in Luxembourg. So they are basically collecting the waste of businesses, restaurants. I mean, it's a professional service. It's not for public waste management. And what we are doing here is to work directly with them so that we can really optimize the way they are working. So for that, the first step was to deploy let's say, sensors into their waste bins so that we can measure in real time the filling level of all these containers and then take the appropriate decisions. And the methodology we had to do that, so here you can just see the platform that has been developed. So basically the methodology we had was to rely on a simulation-based approach. So what we did is to create a numerical model of Luxembourg, okay? And we integrated all the real values collected by the sensors into this simulated system so that it's fully realistic. We also integrated public data, mapping data, and so on. And the result is that, well, we have this simulation system, and this simulation system can generate the best possible route for the drivers of Polygon. So this is the interest of using a simulation system. You can try, you can experiment, you can validate what is the most, let's say, promising approach here. So here you can just see a few statistics, a few, so here, for instance, you have the data coming from a sensor. Here you have, a few information coming directly from the business case. But this is, yeah, basically about it. And then the very last project, but I will not go into details here because this is on my colleague, Kiang. It's a 5G Insight that also relies on a simulation approach. So it's basically for cross-border areas. Here you have complex parameters, and using, let's say, a simulator can really help, since, it's basically about studying security and privacy concerns in, these specific areas. So maybe I will just give you the floor, Kiang. Launch the presentation. Maybe do you have any kind of question on this first part, maybe? So that maybe it's better to manage it like this, maybe, yeah.
For your project,
Maybe.
and the other.
Yes, can you please take the mic so that the online audience can hear you? Thank you.
Hello, my name is Eric Smegens. Yeah, for your project, Emit, I just wanted to know, do you put the constraints of the electrical field into your simulation so that you develop a strategy of RF coverage within, at all places, let's say, a level of volt per meter, let's say, take this unit, in order to look at potential combination of macro cells and small cells?
Yeah, this is exactly where we put the limit, actually. So, well, of course, these are just parameters. You know, when we play with optimization models, and we can change the parameters, we can experiment different strategies. Yeah, the mic, yeah. Thank you. Yeah, so what we are doing is to consider this limit of 3 volt per meter for each radiating element, which is what is in use in Luxembourg. And we consider it as, let's say, a constraint when we develop our optimization algorithms. So this is an ongoing project. This is a project that started in January, and we are currently building the platform that could be then used by network operators, for instance, or regulators. But yes, in short, yes, we are considering that, this limit value in volt per meter.
As well as a combination of macro and small cells?
Yes, this is the objective. Yes, indeed. Which is a bit tricky, but well, I guess this is why this is a research project, basically. Yeah, indeed. Yes.
I just have a question.
Can you take the mic, please?
Sure.
Sorry for that. It's just that we have an online audience. Just checking if we have any question here.
You can speak directly there. Yeah. There's a second. Yeah.
Okay. I just have a question related to optimization of 5G network. Yeah. So did you use any optimization algorithm, or just you use already commercialized software to do the simulation here?
No, we are not. I mean, we are relying on commercial simulators sometimes. We are using open source simulators, but for us, you know, this is not our daily business. You know, we are proposing models, we are proposing optimization models, and then we use these tools to validate these models, you know, under realistic constraints, let's say.
So did you use any practical measurements for the electromagnetic wave?
This is planned. This is not done yet, but this is in the timeline of the project, indeed. Okay. So because we would like, of course, to validate the models that we are proposing here, and basically injecting real data into the simulation tools. I would say that, well, in addition to these models, because just to not be confusing on that, I mean, the plan in this project is really to build a decision support system. So we will actually build a prototype. Okay, this is really the outcome of the project. That will, let's say, use the models that will be then validated by simulation, if this is clear. So we will have an actual prototype at the end of the project. Yeah.
Thank you.
You're welcome.
So you will calibrate your simulation by real measurements?
Yes, this is the plan. If not, this will not be realistic, I guess. Yeah.
Hey, good afternoon.
Good afternoon.
Myself, Shaktivel. I think we met many times on virtual.
Yeah.
So, nice presentation. So just one thing, I understand the objective of this particular workshop is to present the simulation environment. So I also see you initially gave a connected vehicle, connected waste bins. There I try to understand, so today the topic is 5G, so how, I mean, with respect to your simulation experience, when you simulate the 5G with simulation of Sigfox, these two are completely two different technology. So how these two are, based on your experience, how these two are two different technologies in terms of simulation. So when you try to do a simulation, so because I clearly understand this is mainly you want to present all the simulation possibilities, what you have, that's nice. Even you started with the Sumo, the game, so I liked it. So I just try to understand, in terms of technology, so when you want to simulate something, the Sigfox, how it is different from 5G?
Well, I mean, in general, so thank you for the question, very pertinent indeed. I mean, today we have, I mean, it's a matter of model, I guess. I mean, today we can really try to, we can create different types of wireless nodes, okay, and then configure these wireless nodes as we want. We have different tools for that. We can change the frequency band, for instance. We can change the way the node, the protocol stack is behaving. So, well, actually, I think this is what you will see. This is what will be demonstrated, let's say, more or less at the end of the session. But we can change these parameters. The fact that we can simulate 5G, 4G, and so on. Of course, then we need to integrate all the protocols, all these works basically. But yeah, I mean, today you have many models that can, let's say, replicate realistic behaviors for all these technologies. Yeah.
Maybe I can ask maybe in a different way. Can the same simulation tool used for Sigfox, can that be used for 5G? I put this way.
Yes. Yes.
It's possible.
It's possible. Yes.
Okay.
Yes, and you will have a concrete example just after. Yeah.
Thank you.
Okay. Any other question? Okay. And on the online audience, okay, might be a small issue with the streaming. Hope it's back. So in the meantime, I will just launch your presentation. Where is it? Tac. This was this one. Okay, just press the key and yeah, the floor is yours.
Okay, so thanks for coming. So my presentation is a bit different from what Sebastian has done because I would focus more on the security and the privacy issues. The takeaway message I want you to get is in order to solve the security and the privacy issues in the CCAM, simulation would be a key for that. So it's also a quite new approach or a new direction for research. So if you have any opinion, please share with us. So CCAM, from the panel session this morning, I think we all know that it's very popular and it would be an important future area that would involve many players in the ecosystem. So the 5G PPP and also the 5G AA consortiums, they have outlined a lot of use cases for the CCAM. So here I would like to briefly mention several use cases which are from our 5G Insight project. So this project just started a couple months ago, so it's a pretty new project. Unfortunately, I don't have the results now, but only open problems. So one of the use cases is very standard automated LAN merging, splitting, and overtaking. So this project is aimed for the cross-border scenario or the corridors. So basically, in the future, we would like the autonomous or semi-autonomous vehicles to be en route so that to relieve the drivers. And then we want to have technologies embedded in the vehicles and also on the roadside units for the different players to communicate, to exchange information, and to take, let's say, joint decisions. Okay. Of course, 5G is being regarded as the key communication technology in those use cases because we need low latency, we need high throughput, we need let's say the technologies like edge computing, etc., etc. Okay. So the second scenario is real-time traffic flow regulation. So here, basically, we would like to aggregate information to, for example, the roadside units, so that the roadside units could collect the information, do, let's say, data processing, and find out, for example, traffic predictions, so that those kind of predictions could be returned to the vehicles, and the vehicles could take decisions in advance. So here again, the vehicles could be autonomous vehicles or could be semi-autonomous vehicles. So here we have the other use case, which is try to protect the vulnerable road users, so that the roadside units and those facilitated could collect the information from the vehicles and then predict the situations and then notify the vulnerable road users, or to advise the vehicles in order to protect the vulnerable road users. So here is another use case I took from 5G Croco. So it's the teleoperated driving. In this case, basically, we would imagine that there are some drivers who might get tired or who might not be able to drive in the future, and then there would be some experts remotely who are using, for example, 5G to connect into the vehicle and to steer the wheel and to basically drive for the drivers. So in this case, of course, 5G is important to have the low latency and to have the low latency communication between the two entities. Okay, so of course, technologically, I think all those use cases could work if everything is according to the assumptions we would like to make in our research or in our experiment. But if we think about cybersecurity, privacy, and of course the practical situations, I think is far beyond what we could expect. So basically, for our research, we know that complexity is the worst enemy of everything almost. So with the complexity of the systems, we have more security threats, we have privacy threats, and of course those would lead to the safety concerns. And if we have machine learning or AI deployed in those use cases, for example, then unavoidably we need to collect information from the vehicles, and then we would do decision making for the humans. So we would face the trustworthy issues and the ethical issues. So a lot of challenges are ahead. So talking about the practical, let's say, challenges. So here's my example that we have seen a lot of experiments for the autonomous driving, not only in Europe, but in US, in China, or in many other countries. So there are a lot of accidents, and some of them are, of course, the technology is not mature enough, so some failure, but there are other external factors that are falling beyond the assumption or the modeling of the system itself. For example, you won't assume that a bicycle would go to the highway, and you might not encounter this kind of issue in your presetting for the vehicle. And also, from the security perspective, artificial intelligence and machine learning actually is quite a concern. So it's a double-edged sword. So on one hand, machine learning could help us to make good predictions, to predict, let's say, the dangerous scenarios, and to have recommendations or decisions made in advance to avoid those disasters. But on the other hand, to have a safe integration of machine learning and AI into the CCM use cases is very challenging. So, for example, we know that some autonomous vehicles could, let's say, detect the speed signs. For example, there would be 50 zone, 30 zone on the highway. But there are a lot of experiments show that if the traffic sign is modified a little bit, and this sign, the detection of the traffic sign could be going to the wrong direction. For example, if the traffic sign is forbidden to enter, and if you put a sticker on the sign, then it could be decided as, let's say, 120 or something like that. So to this end, what I want to say is when we integrate artificial intelligence in the use cases, actually there could be a lot of unexpected outcomes. And until today, we are not sure what are going to happen because unlike the mathematical, let's say, formulas, but for artificial intelligence, it's really hard to model and to simulate the behavior. And also, I mean, specific to 5G, because 5G is supposed to be the key enabler for those use cases. So 5G is, in comparison to 4G, is a big improvement because 5G has finally aligned to the internet protocols. So, and also, a lot of security technologies have been introduced into the 5G. But on the other hand, adopting the internet protocols is a big risk because we know that we have a lot of accidents. We have a lot of zero-day exploits in the IT domain. So basically, if some vulnerability is found elsewhere, then it can be immediately used to against, for example, the mobility use cases. And then this would cause very serious consequences. And one fact we must remember is for many IT applications, it is normal applications. So if you can't use Facebook like yesterday, it's not a big problem. It won't, let's say, cause a loss of lives. But if you think about this kind of problem happen to the autonomous vehicles, then that could be a disaster. Of course, we could think that, okay, in the design of the autonomous vehicles, we could take that into account, but then this increased the complexity again. So of course, network slicing is a killer, let's say, technology for 5G, which enables a lot of future applications. So that, of course, we have heard a lot that the mobility could be assigned one slice so that we can get all the expected indicators to be guaranteed. But so far, there have been a lot of research done on the network slicing, and there are a lot of vulnerabilities. So although, I mean, in theory, it could work quite well, but so far, it's quite vulnerable. So of course, I mean, we have the more general attacks like denial of service attacks or distributed denial of service attacks. If we think about the mission critical use cases in the mobility, then we would it's not hard to imagine that those kind of attacks would lead to very serious consequences. So, okay, specifically for the cross-border scenario, I mean, the complexity go to another level because For example, for the communication networks, we need to have handovers. So the vehicles, the communication would be going through from one service provider to the other one. And then although we could assume that the service providers could have some pre-arrangement to guarantee that all the performance indicators to be satisfied, but in practice, it's not so trivial, because you could imagine that one service provider could have adopted some really strong cybersecurity mechanisms so that it's very difficult for attackers to get into the system, but maybe the other service provider is lagging behind, and then there could be very serious issues again. So basically, those cross-border scenarios increases the complexity and also causes more cybersecurity issues. So I'm a cybersecurity researcher. So traditionally, what we do is we try to model things. We use mathematics to model things. We build formulas. We try to give mathematical proofs. And then, of course, the condition is we should assume what everybody can do and can't do. But if we think about the use cases we have talked about, it's very hard to mathematically model all those use cases. So we could model something, but certainly for the behavior of the vehicles, the unexpected players and all other factors, it's very hard to have a comprehensive mathematical model to capture them. So, and also, if we use machine learning, or if we want to deploy artificial intelligence, and we don't have data, so, and actually we can't design a solution, put it into practice, and to make it run and to collect data and to study the performance, but we simply can't do this. So basically, for the 5G Insight project, what we have had in mind is we would integrate the simulation technologies into those use cases. So on one hand, we could use simulation to generate the data and to validate the, let's say, the cybersecurity solutions we are going to design. And on the other hand, I mean, in the long term, we might we might use simulation technology to have some kind of close to realistic scenarios to test the solutions. To test the solution by getting, let's say, the humans involved. Humans always make unexpected decisions, so that's an important factor that we should take into account to validate whatever we design for the security solution. So basically, this is my presentation. So it's a bit focused on cybersecurity, but if you have any question on simulation or other aspects, please share with me. Okay, please.
Yeah, please.
In your cross-border project, are you also taking into consideration other modes of transport than cars? For example, trains or buses?
Actually, no, we don't. Okay. And that's exactly the issue, because now even for only the vehicles, for example, on the highway, we are not sure. I mean, if we say that, okay, if we say we want to consider the scenarios where we have the vehicles, we have the public transportation, we have the humans, then it's far go beyond the current, let's say, the capacity, what we could do.
Yeah, let's say that considering the just cars as baseline, I think it's enough for the time being, I mean, for this specific project. But then we can replicate all that to other kinds of vehicles, other, for instance, trains. I mean, not necessarily vehicles that are actually on roads, right? Or yeah.
So that's a remark. So basically, we have been looking into all these mobility projects, for example, funded by H2020. Actually, there are quite some standardization going on, but those standardization are focusing on the standard technologies or standard mechanisms. For example, the communication security between vehicles and the infrastructures, etc. But in all these use cases, in order to make them work, I think people have proposed a lot of other more advanced, let's say, interactions. For example, vehicle to vehicle, and also other stuff. But in those new, let's say, new proposals, security is falling behind because people want to first make something work, and then later on people would question the security aspects. So I think this is the status of this. We have something there, but from the opinion of the cybersecurity researchers, it's not enough.
And maybe as a follow-up, for the other models you had before, on the Belval side, for example, there is a train station.
Yeah.
And you had the buses and the bus stops model as well. So do your humans in the simulation take the train? Because what you have is a BIM, right? So does your BIM include the train or not yet?
This is a perfect follow-up for the next presentation, because you will actually see humans taking, well, not the train, but buses, I think. So yes, this also models human mobility in general, not only vehicles. Yeah.
Okay. Thank you.
For this cross-border situation, do you have collaboration with the mobile operators to let's say, collect data or know the actual setup to anticipate on what's the situation?
Okay, so basically for this project, we are collaborating with a company. It's called Transpolis in France. So Sebastian knows more a bit about this company.
Yeah, it's not, well, it's a test bed, let's say. Well, this is, I don't know if you know Transpolis, it's a test bed in France. Well, it's not the only test bed. But on this one, I mean, this is a test bed that has been built historically by a few universities and I think network operators as well. I mean, I do not have the exact names here, but yeah, indeed, I mean, if the objective in this specific project is to, let's say, collect data to, let's say, validate the models that will be developed so far in reality on this test bed. So in that case, of course, we will need to collaborate with the companies that are part of the test bed. So this is the first answer, I would say. And then LIST is also involved in other kinds of cross-border projects. So for instance, European projects. You probably know 5G Mobix, which has been funded under the same, let's say, call than 5G Croco, for instance. So LIST is part of this project, and well, of course, in there you have companies, you have other institutes. So, I mean, we are not only working, let's say, alone on this kind of topic. I also have to say that we collaborate a lot with the university, with the SNT, for instance, in Luxembourg. So the objective is really to get a realistic picture of the situation, and not only to work on, let's say, isolated models that are not really, applicable to the reality. Yeah, if this answers your question.
So as a remark, I think one difficulty is the scalability of whatever we do. So basically, even for the test bed, etc., we don't have enough vehicles, so we can't really get, let's say, that number of vehicles like on the highway and in the test bed or in any testing environment. For that, we must rely on simulation in this case.
Yeah. So in any case, well, if you all agree, I would suggest to move to the next speaker, since time is running, and well, we have quite a lot of things to share with you actually, if well, this works, of course. Okay, this works. So here, well, it's a technical session. It's really an interactive session. Okay, so there are no slides here. It's
enough with the slides.
It's a showcase.
We are going to see.
Right.
Thank you, Sebastian. So we are going to have a look at a couple of simulation tools that we are using to simulate different kind of solutions, right? So we talked a lot about simulations, right? Well, I mean, my colleague Kiang previously mentioned that a lot of things can be done through mathematical modeling and stuff, right? But then you might ask, well, why do we need simulation tools? Why not implementing this in a real prototype testbed, right? In hardware. And clearly this is like real experiments with real hardware is actually the best solution, right? It shows you how a system actually works. The problem is scalability, right? So when we talk about simulating or experimenting with a couple of vehicles, yeah, that could be done probably by a research institute like LIST or by the university. But when we talk about scaling this to real cities, nobody can afford to buy so many cars and to experiment with so many devices. And this is where computer simulations help. Now, this workshop is about simulating connected vehicles, right? So in connected vehicle simulations, we have two main aspects. We have the mobility simulation, right? And what is that, right? Mobility simulation is how cars move. And here is very important to have realistic mobility models, right? When a car moves, of course, we cannot have cars jumping in front of another, right? So we have to simulate realistically the overtaking and all these real world aspects of a mobility, right? And we are using a well-known open source micro-mobility simulation tool, which is called Sumo, originally developed by DLR in Germany, which has now a wide support by the research community. So there are many people contributing to the simulation tools, right? So mobility is one aspect. And then we have the networking part of the simulation, right? Because we have cars moving around, but then these cars have to communicate among each other, right? And this is where we use another simulation tool, again, open source. It's called Omnet++. And this is only one of the many simulation tools out there that one can use, right? So what I wanted to show you here is for example, what comes into in each of these, what are the different aspects that we have to make sure we have to consider when simulating connected vehicles, right? So when talking about mobility simulation, Sumo allows us to import maps from tools like OpenStreetMap or like Google Maps, right? So we take the roads of a real city, including buildings, including different obstacles. So we import that. So Sumo allows us to import all this information and to try. It's a bunch of XML files that can be then used to simulate a real road network. And then, what else do we need? Well, we need to define the traffic flows, right? So another thing that Sumo requires in input is the traffic demand, and this is what Sebastian was talking about, that it is very important to have realistic traffic demands if we want to represent a real scenario. But since this is a computer simulation, and one of the main advantages of doing this in a simulation is that we can stress the system to its maximum, right? It's something that you cannot do as easily in real life. So, for instance, you can push the number of vehicles to the maximum. You can push the speeds over the limit. You can stress the system until it breaks and see in simulation, right, which is a safe environment, in a controlled environment, which are the breaking points of a system. So in this case, let's run the same scenario that Sebastian showed previously, right? So it's the Belval and Esch scenario here. So as you can see, there's essentially the real roads taken from OpenStreetMap, and we can zoom in and up to, for example, these H are the bus stops and everything, and we can simulate to this level of detail. Also the traffic lights, so these green and red rectangles here, they represent the traffic lights, right? So what we can do is to run this simulation, and we will see now, let me slow down this a bit, right? So we can see now vehicles moving according to some traffic demand that have been previously defined, right? And in this case, we have to answer your previous question, right? So we also do simulate pedestrians. Let me see. Here we can see a person waiting for the bus over here, right? So again, the simulation of people is also based on some traffic demand. So somebody needs to give us this data, and then we can transform it into a simulation model. Now, at some point, just to show you here, we have the roundabout. I don't know if you're familiar with Belval. This is the roundabout in front of the university, and then we have the big roundabout that connects it to the A4, right, and highway and to Esch and so on and so forth, right. And then we have the railways here. Yeah, we do have a train, which is currently stopped, and as you can see, there is a passenger in front of the train, right, in one of the wagons. Probably this is a morning scenario, I would say, because I don't see so many people. Yeah. So let's see. Yeah, exactly. So in this bus, for example, we have 7 people driving, and you can see here, just the light just turned green, so cars can move. We also have these smaller things are motorcycles also simulated, right? So there are different types of vehicles that can be simulated, right? Now, I will not stop too much on these mobility aspects because this has been discussed already. So I will move to the next aspect of the connected vehicle simulation, which is the networking aspect, right? How do we, so now we want these cars to communicate, to coordinate between us, to send messages to each other, and then take decisions based on that. So here is where we use another simulation tool that is called Omnet++, right? And here we have, so Omnet++ is a discrete event network simulator that essentially simulates, so when we talk about communication between computers, between cars, we have to simulate different communication protocols, right? You probably have heard about TCP, IP. These are just some of the communication protocols, but in 5G there are many of them, and each of these aspects have to be accurately simulated. These models have to be implemented and considered in our simulation, right? So what I'm going to show here, for instance, is a smaller scale simulation of just an intersection, right? A road, a small intersection with cars driving from north to south and from east to west, while communicating using the 5G network. So, but the cars, remember, the mobility of the cars is simulated by Sumo, and then we link the simulator to the network simulator. So every car that in Sumo is a car, in Omnet, this is a network node, a wireless network node, with all the aspects involved, right? So let's have a look here. Let me run the simulation. So, for example, we can see here a very simple scenario with 2 you know, with 2 base stations, right? And we have a server somewhere in the cloud sending some data, well, at some point to the cars. Now, the cars are not yet visible. Let's run a little bit faster the simulation, right? So we see now the 2 cars entering the simulation scenario, right? Now, as I said, and you can see the server sending a message, right, a packet that is first sent through the network to the base stations, and then the base stations relays these messages to each of the car, right? And so what is a car in this case? Well, I mean, we can actually have a look inside and see what is being simulated, right? So let's take just the first car, right? Let me just make this a little bit smaller. And remember when I said that we simulate a bunch of network protocols inside? So, you know, the network protocols are grouped in different layers. So you can see here the 4 main layers. We have the link layer, network layer, transport layer, and application layer. And this is what is inside every car, right? And at every layer there are, again, a number of protocols that have to be considered when sending the messages, when receiving the messages, with what probability this message will be received, and so on. And as you can see, there are already some metrics like how many packets have been passed up to the application layer, right? When I talk about an application, I don't know, an application can be your browser. Well, in this case, some safety applications, because we talk about cars, right? So a safety application, meaning, I don't know, an intersection, a collision avoidance system, right? That is the application that needs information from cars around, their position, their speed, and this information needs to be exchanged frequently so that they coordinate to avoid collisions, right? Same here with the server, right? So we can look inside at what. So we can see here the car 0 receiving messages that are being sent by the server, right? So exactly. So then, of course, we see there's a nice graphical representation of how the communication process happens, and this allows us to go deep into the different aspects of the system and to see where the problems are. We can, as I said, we can simulate different data rates. We can simulate different communication frequencies. We can simulate different cars, right? Implement different applications on top, and then see both the network impact on the mobility, right, and vice versa. The mobility, like the number of cars, will be the impact on the network, on the radio access, on the 5G network, how much it will stress the network, right? And of course, what do we do with these simulations? Well, we run the simulations, and then we collect we can collect some statistics, some metrics regarding the number of packets that have been transmitted, and so on and so forth. And then we can plot this, right? So this is a nice tool that allows us. Let me stop the simulation and then say, okay, we run the simulation in the end, and then we want to plot to see where the results of the simulation. So actually I have here another simulation that I ran previously of exactly the same scenario where cars were sending periodic messages. So just to give you an example of what kind of data we can get from, right? So we just run the simulation, and we can see here, well, on the y-axis, we count the number of messages that have been sent or received. So in this particular case, car 0 is the sending, is the sender, and all the others are receiving. These periodic alert messages, right? And so the blue bar represents the number of messages that have been sent, and then we can measure on each of other cars how many messages have been actually received, right? And you can see that, of course, some different cars receive different messages. Why? Because we are realistically simulating the path loss models, the errors, because messages can be lost because of obstacles, because of propagation loss, because of bit errors, this also depends on the distance from how distant are the cars, the two cars communicating. So the farther away you are from the sender, the least the probability that you will correctly receive that message, and so on and so forth. So we can measure that, plot that, and see some nice results. One other thing, for example, that we could look at. Well, we talk about alert messages, right? So how fast do these messages arrive from the sender to the receiver? We can measure that, and we can see that this is a matter of few milliseconds. Here we talk about, 14, 15 milliseconds generally, and then we see some fluctuations, right? On the x-axis, you see the simulation in time. So this is the seconds on the horizontal, on the x. On the y, you can see the message delay, right? So how long it took for a message to get from the sender to the receiver. And this is measured in seconds, which means 0.020, that is 20 milliseconds, right? So, and then here we can, let's disable all the others and let's have a look at the one car. And then the idea is that really when we run the simulations, we see, we have some big fluctuations here, right? So what happened at this second 40, that instead of our usual, our usual 14 millisecond, we got a message that has been delayed to more than 60 milliseconds, right? So these kind of tools allow us to go deeper into the system and to see where the problem is, what was the reason, has there been an issue, right? And this kind of activities, and we as researchers we use these tools to build, for example, when you mentioned, well, can there be another technology simulated with this tool? Well, this is a network simulator. You can implement any communication technology as long as you have realistic physical models, right? Regarding the path loss propagation. So if we have an input these kind of realistic models, then we can plug these in, and then we can implement on top the different aspects of the protocol stack, right? And many are already available, right? Such as we have simulations of Wi-Fi, Ethernet, a number of protocols, VoIP for Skype. These kind of things are already available. So let me then just quickly switch to a real use case, because we have seen now some aspects of the network simulation, but then let's look at a real use case, right? Of probably one of the most popular and one of the first connected vehicle use cases that we will see on our roads is platooning. Now, platoons of vehicles are just convoys of vehicles driving on the highway at high speeds, very close to each other, right? So the idea is that by allowing, if we include the connectivity, so the vehicles can send messages, 10 messages per second, for example, and exchange information among each other, we can have we can have this kind of platoons where vehicles are able to travel autonomously, right? Very close to each other. And of course, you might ask, why do we need that? Well, there are many advantages of having platoons, including if you're a company that has trucks and delivers goods from point A to point B, and you have one driver just driving the first car in front, and all the other cars behind, they are just controlled by wireless communication. You don't need, we exclude the human driver from the cars behind, which allows us and by driving close to each other, we eliminate this air resistance, right? So then increases the fuel efficiency, and also it's manages on a larger scale to improve the traffic efficiency, because by having cars driving close to each other, we can enter more cars into the highway on the same road with respect to human drivers, right? Instead of building larger roads, and then we can use the same roads and let more vehicles flow. Let's very quickly see a short simulation of a platoon. And why I'm mentioning this? Because what I want to show you here is the difference between having such a platoon with current systems that we have nowadays in the cars, right? We know adaptive cruise control. You know adaptive cruise control. Probably most of the modern cars have already these. So an adaptive cruise control relies on a LiDAR or some sensor in front that measures the distance to the vehicle in front and allows you to drive and quite close to the other vehicle. And if the vehicle in front brakes, the car behind will detect that, right? And it will brake in order to avoid accidents, right? But clearly, since we talk only about line of sight connectivity, right? So you only can see the car in front. You will see that in a platoon, this is not really is not working so well, because as you will see now, there is this accordion effect, right? So if you have I don't know, n vehicles, 8 vehicles very close to each other, and then the car in front starts oscillating, accelerating, decelerating, you will have an accordion effect, right? And this creates dangerous situations. And I want to show you what happens when we have this classical system, and then what happens when we have connected vehicles, namely the same simulation, but in this case, cars exchange messages using 5G wireless communication, 10 messages per second, right? We can send this message very frequently, and they can coordinate in order to avoid this kind of accidents, right? So let's have a look at this example, and we have in this simulation, 8 cars? Right, we have 8 cars, so let's run this first with an ACC, a classical ACC system, right? So here I'm going to show you, right? So you see already the two simulations connected. This is the Omni, the network simulator, and then we have the Sumo, which it will start shortly, that simulates the mobility, right? So let's start the simulation. We have now these 8 cars, right? And at second 5 or 7, the first car starts braking. And you can see the others detect this and they start braking as well. And, well, unfortunately, the 4th car didn't make it, right? Because clearly, the cars, again, the cars have different different manufacturers, so different characteristics. A car is able to brake faster, another car is able to brake not so fast, right? So because of these things, in this case, well, it was too close, right? So it didn't make it. Now, I think in this simulation, the starting distance between the 2 vehicles was 8 meters. So clearly, for a current ACC system, 8 meters of distance is too close. It won't work. Of course, if we launch this, let's launch the simulation and say, well, let's increase the distance. What happens, right? So we can launch the same simulation, again, a classical ACC system, but in this case, we let more distance between the vehicles. And you can see that, yeah, I will. Okay, so all 8 are there. Again, the first car starts braking. the others start braking as well. As soon as the ACC, the LiDAR, the sensor in front detects that the car in front is braking, right? So clearly this shows, yeah, what can we do with this? Well, we can find using a current ACC system, what is the sweet spot, or like what is the minimum distance that we need to keep in order to avoid accidents in this kind of automated systems. Now let me show you the same thing, but in this case when the cars communicate between each other. And in this case we have a CACC system, which is a cooperative adaptive cruise control. And in this case we will see, we even decrease even further the distance. So we talk about 5 meters between two cars, even less than in the first case, right? And let's have a look at this case. So you can see cars are very close to each other, and then it's at 5, right? So here they all start braking instantly. What does it mean? Well, because as soon as the first car started braking, it sent messages outside 10 times per second saying, I changed my speed, I changed my acceleration, right? And all that happens using wireless communication. Since we talk about 10 messages per second, this is not even, with the human eye, you cannot even notice that there is a short delay between the first car starts braking and your car starts braking. But what we see is that they act as a platoon, as a train. So they almost instantly brake together. So clearly here we saw only, we had a look at the, let's say, the application from okay. I wanted to stop this. Does not respond. Because again, as I said before, we can collect some statistics there regarding message delay, regarding and the speed. So let's have a look at some of these statistics, right? So in the plots that I'm going to show you now are from another simulation that I done, not the braking scenario, but I run another simulation in which the platoon leader oscillates, right? Does a sinusoidal, has a sinusoidal behavior, right? So it accelerates and accelerates, decelerates. And what we want to see is how the other vehicles move with respect to the car in front, right? So in here, we can compare directly. Let's have a look at what do we have here, right? Let me see if I can. So I've measured here the speed, the distance, and the acceleration. So let's have a look at the speed. The speed in time for each of the 8 cars, right? And you can see this sinusoidal behavior, right? So we can have a look at, this is the first car. This is the platoon leader, which is the first car in the platoon. Ideally, we want the shapes of all the other speed measures to overlap, because that would mean that the platoon is consistent. Instead, with a classical ACC system, you see this difference, right? And that is clearly not what we want. And we can compare this with exactly the same scenario, but for the CACC system. And this is exactly what we want, right? So exactly the same scenario, exactly the same parameters, but in this case, the cars are connected, and this is what we can obtain, right? So as researchers, there are many aspects that we investigate in there by changing how many cars are driving on that highway, what is the impact on the human-driven cars on the platoon, and then how we form this platoon, right? How joining a platoon works, how leaving a platoon works, and so on. So this is just one example of an application that uses connected mobility. What else have we? So, for example, another thing that we can see here is the distance, right? What we did, we measured the distance between every 2 consecutive vehicles, right? So you can see that in a classical ACC system, the distance never converges. Actually, the first car is not needed because the first car doesn't have any distance to. So, and you can see that the distances, they vary during this simulation, and they are clearly not consistent. So that there is this accordion effect. When we look instead at the connected use case, you can see that the situation is different, right? So you can see now that the oscillation, so they oscillate around 5 meters. So they are basically at the same distance between each other. Yeah, so with this, I would like to conclude and to let you ask some questions if you would like to ask. Yes, please.
Thank you for the presentation.
Can you take the mic, please?
Thank you, yeah.
Thank you.
Really exciting presentation, thank you. I'm wondering, in platooning scenario, and I'm working in this industry, are you also considering the load of different trucks? Because that's one of the challenges we have, because obviously the braking time or braking power is different when you have the different loads of the trucks. So then the platooning, you know.
Right. I mean, maybe not the load specifically, but we can simulate the load by acting on other parameters, like the braking time, right? Or that by considering the load, we can then manually compute, okay, how long it will take then to brake having this kind of load, and then we input this into the simulator and say, okay, in this case, this truck has this level of load, which in simulation means this braking time, right? So this can be considered indirectly, not the load specifically, but through other parameters.
Understood. Thank you.
Thank you.
Just one question.
Yeah.
So my question initially was about, can this be possible with 4G?
Yes, absolutely. Yeah.
My question is, how this is different? Because I see two different simulation environment.
Right.
So how, first of all, these two are interconnected?
Yes. So Sumo.
Just imagine this is a research project.
Yeah.
When somebody wants to implement it,
Yeah.
in the company's perspective,
Right.
how can this be possible, feasible? And that's the question number one. And question number two, to me, I mean, this also, I mean, the scenario which you've shown between the 2 vehicles to exchange the data, this can also be done with another technology, need not be 5G. So when it comes to a simulation perspective, how different for 5G? Because we are talking today about 5G. Yeah? So what makes this 5G to be special when it comes to simulation?
All right. So let's let me try to answer your first question. The first question was about how we put together the mobility, I assume, and the network simulator, right? So. Of course, through available tools that each of these simulations offer. So in this particular case, Sumo acts as a server that you can implement your own client and interrogate. And essentially what you do, you ask, give me the position of every vehicle in the current scenario every 10 millisecond or every 100 millisecond, right? And what Sumo does just answers you with a list of vehicles, the list of cars, and their positions. What you do in the network simulator then, you take that, you parse that list, and you say, okay, these are my network nodes. Right.
These two are connected. And is it now, today I see it's more manually you are doing, or is it something automatically the Sumo, there is an interface between Sumo and to the network simulator? I mean,
there are tools available. So, for example, we are using one very popular tool, which is called VANES, Vehicular in Network Simulation, which does one of the main, let's say, purposes of this tool is actually to link automatically Sumo and Omnet, right? And does exactly this. It provides a bidirectional communication, so you can get the nodes from Sumo in Omnet through this tool, and vice versa. So let's say you want to implement an application where two cars communicate, and as a consequence of this communication, the cars have to change the route, right? So then you need vice versa communication. You need to inform the Sumo server that now it has to change the path of so that is also possible, yeah.
So, coming to the second part of the question, so what makes the 5G to the special? When it comes to simulation, so what is the difference between simulating 5G and simulating any other technology?
Well, the main difference is
the network parameters. You change the network parameters.
But the actual the technology itself. So the protocols, right? Because I don't know, Wi-Fi works in a way, right? And cellular communication works in a different way. What do I mean by different? Well, it uses resources differently, right? The channel. Yeah.
Or the opportunities the simulation can bring you. See, for me, it looks the same can be the techniques that we use like 4G. Okay, so that means I take your the simulation environment, just change the network stack.
Right.
Instead of 5G, I apply 4G. Still, it works.
Yeah.
I'm trying to understand. We are talking today the simulation to minimize, like you said, you cannot emulate or the real-time scenario.
Yeah.
So this is not possible. That's where you are going to do this project. It is mainly the simulation possibilities. But I'm still not convinced, at least with respect to 5G. Okay, is it something special to be considered?
Well, but this I'm not sure if this has something to do with the simulation aspect. It's just a difference between two different technologies. 5G redesigns the physical level, brings more throughput, more lower latencies, and these aspects are simulated here. So one interesting thing that you could see in simulation is actually taking the same platooning scenario. On one hand, you can take 5G and simulate using the 5G technology. Then you can take 4G technology, simulate exactly the same scenario, and you can put on the same plot and see what is the difference in terms of delay, message delay, in terms of throughput, in terms of data rate. Right. But this is
comparing the two technology. Are there any differences?
Of course, but this is exactly what I mean. What our industry partners are presenting downstairs. These are not lies. These are real measurements that I did. So of course, higher data rates, lower latencies, right? So all these benefits you can see from the 5G technology.
So just with this in mind, I would like to close the workshop. I'm sorry for that, but we're already a bit late.
Some insight in what the question has been here.
Can we have this
because all what you
quickly
describe is actually extremely time sensitive.
Yes, absolutely, absolutely.
The difference with 5G is that it's oriented to be time sensitive networks, propagating clocks. So maybe that would be a topic for further discussion.
Absolutely, absolutely, yeah. Thank you. Yeah.
Thank you. Was pertinent.
All right, we can take this outside and continue. Yeah.
So with this in mind, I would like to close the workshop. Thank you very much to all of you. Welcome.